Hello, it's James from XRobots.co.uk. This is part 7 of my BB-8 version 3 build, which I've got just here. If you want to check out version 2, who's lurking around in the background, there's a 10-part series in my channel. There's also a 5-part series for version 1, which I built before that. So last time I built the head mechanism for this and the magnetic coupling. Before that I built the head control arm, so most of the mechanics is built now. I may be revisiting some of those bits to do some minor tuning, depending on how it works when it's in motion, but we're not going to know how that's going to work until we actually build some electronics and do some coding. So this time I'm starting with the electronics, starting with the remote, and also looking at the inertial measurement unit, which is going to stabilise the whole thing electronically. So let's get straight into the electronics. This is the controller from BB-8 version 2, which is basically an Arduino powered controller. So I've got an Arduino Uno in there with a Bluetooth shield on. I've got a LiPo powering it, 2 joysticks, a 5th channel on this knob, and then I've got 2 buttons. One's a latch switch and one button that activates the sounds. And I've used Bluetooth for everything so that in the future I can write a phone app, and of course I can then write a Bluetooth phone app to connect to the Droid. So I'm going to carry on with Bluetooth again. This is a bit big though. It's not too bad. These joysticks aren't very good. They're about £10 off eBay, but they don't center properly all the time and they're quite stiff. Also I need 6-axis now, so there's an option of course to, you press a button and then a joystick switches over and does something else. What I really want though is the 2 joysticks for driving, and then I need to then be able to turn the head and then spin on the spot. And it's kind of tricky to do with these extra knobs, and I might want to sort of reach over and do things at once without having to remember how I've toggled switches. So my approach this time is going to be to use more joysticks. So I'm going to use these little thumbsticks that you get, a bit like PlayStation controllers. You can get these pretty cheap on eBay. And I'm going to use 4 of them. So I'm going to have 4 of those in a sort of thing like that. I'm going to have 3 press switches, not sure what they're all for yet, and 3 toggle switches. And I can have pretty much as many digital ins as I want, as long as there's enough on the Arduino, which there are. And there'll be 6 channels on a normal Arduino of analog, so I can have my 2 2-axis joysticks for driving and moving the head around, this one for turning the head, and this one for spinning the flywheel. My controller's going to be a bit smaller this time, so this is actually a battery I'm going to use, which is a 5 amp hour LiPo, and it's a USB boost adapter, so 5 volts comes straight out that I can plug into the Arduino, and it's also got a battery monitor level thing on it as well, and that seems to work quite well, so I think that's going to last for ages. And pretty much the controller's not going to be much bigger than this, so it's going to be more like a gamepad, with the 4 joysticks on, sort of mounted like this above it, and then the switches along the front. And in order to get the Arduino and everything in, I'm actually going to use a much smaller Arduino called an Arduino Nano, and that's what I've got on here. There's also a Pro Mini, which is even smaller still and has no programming socket. And the Bluetooth board I'm using this time is on the other end of this cable, so it's this. So all of the electronics are going to be only this big, which is much, much smaller. So I've just powered that up. The Nano there is powered from the USB power pack, and that has got the same code running as last time, which is just transmitting analog and digital values. Obviously there's nothing connected, so it's just sending pretty much ones for all of the pins that aren't pulled down and various random floating analog values. It's transmitting on Bluetooth, and I bought this pair of Bluetooth chips, which are actually already paired at 115k baud serial. I got those off eBay. You can get them and configure them. They've got the little switch on for putting them into AT commands mode like I did last time, but basically they pretty much worked and they didn't cost very much and they're really small. So I've got an Arduino Uno here, and this is plugged straight into my PC, which is down there. Now what I've got here is a reset wire, so I've actually reset the Arduino and I've swapped around the RX and TX. So what I'm actually using is just the FTDI USB to serial chip, so the Arduino is not doing anything. This is basically just taking the data coming over Bluetooth as a serial link, shoving it straight in the USB to serial port. And I've got another camera which is over here, which is looking at the values on the screen. So we can see those values going past, and basically if I go and just touch the analog pins on this Arduino, so they're all floating, so if I touch them you can see that the values change that are being received, and basically this is sending data around 25 times a second, Can't quite influence the digital pins, but there we go. But you can see the data changing there. And of course this whole thing is wireless with Bluetooth, so if I pick this up and take it away over here somewhere, so PC's over there, we can still see that if I mash those pins, hopefully you can see that data changing, so that seems to be working. So I just want to talk a bit about the inertial measurement unit I'm going to be using for electronic stability in the Droid. So I used one last time to have stability driving backwards and forwards, but of course it had no side-to-side axis, and this time it does. The inertial measurement unit I'm using is this, which is an MPU 6050, which are really cheap. They normally come on a breakout board for about £5 in money. Last time I used a BNO 055, which did some of the maths for me on board and just gave me the angle. And this one almost does too, although it's not actually officially supported by the manufacturer. So someone at MIT has kindly reverse engineered it and written a library called I2C devlib, and it's part of that, the MPU 6050 library. So you can just get a piece of code which uses the processing on board to combine the gyro and accelerometer. Now importantly, this one doesn't have a magnetometer, which the BNO 055 did. The magnetometer got really confused last time by all the spinning metal and motors in the Droid, so I had some issues. This one only has the gyro and accelerometer, so it should be much better. Now I've got, again, the other camera is pointing at the screen over here, so if I tilt around the inertial measurement unit, then we should find that those values change and it gives me the answers in degrees. So there we go. So that is pretty good, and there's also some other clever stuff going on where it's using an interrupt pin and it's using the hardware clock on the chip, and the interrupt pin so it always runs the loop when it wants to, and the timing is locked to this chip, but we'll talk more about that later on. Alright, so I'm going to 3D print a transmitter again for the electronics, so here's what I've come up with. Thought I fancied a blue one this time, so there we go. So the joysticks obviously mount on there, and then I've got space for various buttons along the top edge. So what I've done is left a hole in here, and eventually there'll be a display in there or some LEDs. So I'm hoping to send some serial data back from the Droid so we can look at fault conditions, possibly battery life, that sort of thing. So for now I'm just going to leave that panel open and I'll stick something in there in the future. But for now I'll be able to see where the Arduino and the Bluetooth board are so that I can see what their status is, and those are going to be just below there. Here's the base, so I've mounted the joysticks on. Obviously the top plate goes on and screws on, and there's space in here for, I've decided, an Arduino Pro Mini in the end, purely because it's got 8 analog ins, so I can in fact wire all of the 8 analogs in if I wish to use these joysticks for the other axis in the end. And that's the Bluetooth adapter, and I'm just going to obviously link the pins, and then I can hack into that serial link with something else as well if I want to. So I need to solder all of those up, and hopefully it will transmit the same data. Right, I'm getting there, so I've got the things fitted in. Most of the axes are wired into the analog ins, and I've got this wire to the switches, which I'm mounting on the front panel here, so they need to be wired in. USB power comes in through this USB tail, and I've got a little strain relief. I don't know if you can just see, there's a knob in there with it wrapped around with a cable tie so it doesn't pull against the electronics. And that's wired into the Arduino, and the Bluetooth module is there, and I've got those push connectors still on the modules so I can hack into that if I need to, but it probably won't. Alright, so I get the other switches wired on, then we can give it a test. Right, it's all together, here it is. So these are the joysticks that are full function, those go sideways only, and I've got a number of toggles and switches. And I've just stuck the battery pack on the back there. What I'll probably do is make a big Ninja Flex kind of case for this, printed in rubber, so that'll encase everything. Obviously the USB port sticks out of this, which is a bit nasty, but it gives me access to plug it into something else if I run out of battery power, and I can charge my phone off this if I get desperate. So if I show you the screen again and we power this on, we should find it pairs and data starts coming out on the terminal. So let's see what happens. There it is. So it's the same data as before, and if you can just see that, let me zoom in slightly. So we should see all the values for the analog and digital. Hopefully you can see the remote at the same time. So you'll notice there's lots of ones on the end, and if I press those all go to 0. And those are the 3 toggles on the very end of the data there. So those are all my digitals, and the rest are all stuck at about 500, which is in the middle of a 10-bit range, which goes from 0 to 1023. So if I move this one, we should see the first digit there changing from 0 to 1023. That's the second digit, the third one, and then these two will be the fourth and fifth and sixth, I should say. So that means everything's working pretty much, and if I wiggle lots of them at once, we get all of that data being pumped out at 25 times a second. Right, the code for this is pretty simple. I've declared various variables there for the digital and analog things as integers. I've got a variable here called previous millis, and what I'm using is effectively the multitasking code to check this runs exactly the right time. That's running at 40 milliseconds, which works out at 25 times a second. So if you have a look at the Adafruit examples for multitasking on Arduino, you can find out what this is about. But essentially it's instead of using a delay in the code to do the timing, it's actually timing milliseconds and running this when we get to exactly 40 milliseconds, so it's locked pretty well to 25 times a second. And simply all it does is read the digital and analog values, and then it prints them all to serial, and that's it. And at the other end we'll strip out these serial values and put them all back into variables. So the basic plan for this is that I've got data being transmitted here, and that's happening at 25 times a second, so that's happening every 40 milliseconds. Now I've got my MPU 6050 here, and this has got its own timer, and as I said, it's using the interrupt pin on the Arduino to run the loop. And I've hacked the library, I found some stuff online. Default is 100 Hertz, so 100 times a second, but I've hacked that down to run its main loop. That's going to run at 50 times a second. So basically that's running faster. The main loop on the Droid is locked to this hardware timer, running faster, twice as fast in fact, than data is being sent from here. So what will happen is, every time it sees some data, it will update the variables, and then it will go round, which should be roughly, of course, once every 2 times it goes round, so every other time. If there's no new data, it will leave the data alone. I'll have a safety mechanism, so if I turn this off, or it gets disconnected, and no data is received for, say, half a second, then it's missed quite a few cycles that it knows something has gone wrong and there's an emergency stop, or some other fault condition appears that's there for safety. So that's pretty much what I need to do. And this has got a FIFO buffer, so this has got a first in, first out buffer, which is basically a pipeline where data goes in and then it goes along the tube and comes out the other end. And if the buffer goes wrong and overflows, it resets. So I have to be quite careful that my main loop will run 50 times a second. There's various ways I can time that to make sure all of the other stuff in it runs within that time and the buffer doesn't overflow, because that's going to cause some problems. Similarly, that's why this is sending data at half the speed, so the UART buffer doesn't overflow, which is on the serial receive of this Arduino. And this is an Arduino Mega, which has lots of serials on, so I can keep one for programming, and there's another 3, one of which will be connected to the Bluetooth receiver, which will receive data from the transmitter. Let's quickly look at the other electronics that are going to be associated with this. So we've already got obviously the transmitter transmitting over Bluetooth, the Bluetooth receiver, an Arduino Mega receiving that data over serial, with the MPU 6050, the inertial measurement unit attached, which we're going to use to help keep the Droid stable electronically. So have a look at version 2 for an immediate answer on roughly how that piece works. This has more axis to stabilise, but that's fine. But we need some more stuff in the Droid really to drive the motors, so I'm using windscreen wiper motors largely, which I'm running on 24 volts, and the stall current of those is around 15 amps. I'm going to need some bigger motor drivers, so these are BTS 7960s, which will do, I think, nearly 30 volts at 40 amps or something like that. They've got a big heatsink on the bottom, and I can drive those with PWM straight out of the Arduino, and I take power in there and the motor out, and they'll handle the currents that we need. And I'm also going to need some quite thick wire to drive those, some fuses, some switches and things like that, and these need to be mounted in the Droid. And I've got 3 because I've got 3 axes, so I've got driving backwards and forwards, leaning left and right, and another one to spin the flywheel when I eventually fit those motors. I'm going to need to handle quite a bit of current, so I bought some wire. This is silicon wire in various gauges. I think that's probably too thick, probably that's okay. and that looks about like what's actually on the motors, so that would probably be okay. And I've also got this blade fuse, which is a blade fuse holder for a 25 amp fuse to go in there. So you cut the wire and then you can fix that either side. I've got some various connectors, switches, so I can switch off each stage of the robot. So we'll be switching each of those 3 motor controllers independently and switching the batteries off completely. And I've also got some of this terminal strip, which is this really old school stuff with Bakelite. So I can take my batteries on, I can put the switches in, I can put the fuses in and basically do power distribution. Now the batteries themselves, last time I used 2 amp hour LiPos, and I used 2 of those in series to get 24 volts. Another one for powering the head arm and another one for powering the electronics. But they go flat really quickly, and I've got the extra motor this time. So this time I'm going to be using 5 amp hour LiPos. So a pair of them in series, which will give me 24 volts. Now I still could use a smaller one to power the electronics, but I actually need the mass in there. And I think I need one of these again to power the head control arm with those servos, because they're quite power hungry. So I need to balance the droid up so it's balanced on left and right. So in fact what I'm going to do is then add a 4th one of these, so I've got 2 sitting either side of the trousers. 2 of these will be paralleled up to give me a 10 amp hour 11.1 volt pack. That will power all of the electronics and the head control arm, and then the other 2 will power the motor in series. So these are a bit overkill really. I could have gone for 7.4 volt LiPos because I only need 6 volts to drive the head control arm and the electronics. And you can get them which are basically 1 cell thinner, so these are 3 cell LiPos. So you can just about see on the side there the divisions. So you can get ones that are only 2 cells, but they're not that much cheaper. Then I'd need a pair of them which are different to the main drive ones. So I just decided in the end I'd just use all the same batteries and some power regulation for the things that need 6 volts. Then I can charge the batteries whenever I want and swap them around, and they'll all be universal for any of the roles. Then I've got further power regulation, so I've got these power regulators which are for radio control applications, and these are 5 amp regulators that come down to either 5 or 6 volts. Each servo is going to have its own one because the servos draw something like 800 milliamps off load. So each one's going to have a 5 amp regulator. Then there'll be another regulator to power the Arduino Mega on something like a 5 volt 2 amp regulator, and all the other 5 volt stuff. It doesn't need anywhere near that, but I happen to have some adjustable regulators that are rated at 2 amps. So I've got quite a lot of stuff here which all needs to be actually fitted inside the Droid. Let's think about how those things are going to be mounted in the Droid. So I've still got some specific things missing, which are mainly the motor to drive this flywheel round to spin on the spot, but that's all it does. So I'm not too concerned with that at the moment. I'm more concerned with side-to-side stability and back-to-front stability. So the motor to drive this flywheel is going to go down in there, and I've got more than enough space, more than I had in version 2. And there's also space at the other end for a second motor if I need 2, which is what I did last time. So I know that's going to fit and I know it's going to work. I have to mount all those motor drivers, the batteries and the electronics in here somewhere. So my plan is to mount the batteries, a pair of them, either side of the trousers. So this whole mechanism leans side to side to stabilise, so I want to take the batteries with it. So I'm going to mount those in there with another one in front, so a pair of them mounted like that. And I need to avoid the mechanism for actually tilting this side to side, which is this toothed track and the toothed rubber wheel. And in the other side of the Droid there's even more space, because all I've got is the motor there. I haven't got the track, so I can easily get another pair of batteries in there, although I do need to be careful that as it tilts the track can come up to this side slightly. So it looks like these motors are just the right thickness to fit in if I make a minimal bracket. I'm probably going to mount my Arduino somewhere up in there on a long cable so it can be pulled out for access, or somewhere down here. It could go up here, but I still need to mount those motor drivers, so I think those are going to be mounted onto this on a plate either side, so I can get 2 there. I could get the Arduino on there as well. There's actually plenty of space. They weigh a bit because of the heatsink, but not so much it's going to upset it. Obviously I've got heavy batteries and the drive motors for the flywheel to go down to keep the mass low. So let's get some brackets made. Let's have a look at the battery mounting plan. So let's just hide some things. I've got these clear things here represent the batteries, which are roughly the right size, and I've positioned those in the right place and then made the brackets around them. So if I get rid of a few more things, we can see there's some purple bottoms here which actually hold the batteries in. They're like little pockets on each side, So they rest in, and those are going to be solvent welded onto the trousers. So if I get rid of this, you can see in fact this piece is at an angle, and that's to take account of the motor bracket which drives the trousers side to side. So one of these has got a cutout and the other one hasn't, and both of them have got this kind of thin wall so that the battery sits in there nicely and can be attached in with an elastic band or something. And at the top I've got some stoppers, which are these, which stops the battery falling down. And then I've put these hooks on. So the plan is to put a piece of elastic band or something around the bottom of the, or around the middle of the battery below the yellow part, and hook that around onto that hook so it holds them down and it holds them in. And then hopefully they shouldn't go anywhere near this mechanism. The batteries pictured here are a bit bigger. I've left a bit of extra space, but in real life they do fit quite neatly to the side of this. They do just fit in here. So let's get those parts printed and fitted in, and hopefully that will help. And of course having the batteries quite low down gives me more stability and more force over the main drive wheel, which is of course off centre. So hopefully you can see those parts fitted. There's a block there and there's one right down in there that the base of the battery fits in. So if I just slot those in, they push in fairly snugly like that, and I've already fitted two in the other side to keep it balanced. Now the plan is to put a bungee around this, take it underneath here, and actually put this hook on the side in the end instead of on top, so it doesn't hit the bottom of the servo, which is just there. So the plan is to wrap a bungee around and hook it on, and that should hold the batteries in that direction away from this wheel and this track. And I've checked all the clearance and everything's fine. It clears the main drive motor and the wheel below. I've also added these pieces on, which I've just solvent welded on. They've got screw holes in to hold this panel, and this panel is going to hold the electronics. So on one side I'm going to have two motor drivers and the piece of power distribution strip above them. The other side will be one motor driver and the Arduino next to each other with half a power strip. And that works as well. I've checked the clearance. When the trousers move, it doesn't hit the edge and it doesn't hit that wheel. So that's looking pretty good. The inertial measurement unit is going to be on top of there, but I just need to print some brackets to hold these, because they've got these big heat sinks on the back, and to hold the Arduino. I've printed these little supports which are for mounting these. So these have got flat bottoms that are slightly wider, and they'll go like this, and I can screw them on, and then I can solvent weld these down to those other plates in the correct place. And I've also printed these little things which are little feet for the Arduino, so I can screw that down to the mounting points and then mount that by solvent welding it to the last part. Right, so these are bungeed in now, holds them in place quite well. I've got my bit of strip on here, my panel mounted, and now I can mount my motor drivers. So I'm going to get two on this side, one on the other side with the Arduino. So obviously I've printed these stilts. I didn't print them into this because this is the bottom of the print, and obviously the top is a shape to fit that piece of the trousers, so that's why I've made these separately so I can stick them back to back. And they'll mount on there, and I've already tested moving the trousers to check this doesn't hit the ball or anything else, and it's fine. And it's fine with the Arduino on the other side. So I'm going to get out some acetone and stick a pair of those on there. So these are mounted in here. I've got my two motor drivers, and I've solvent welded their stilts onto that platform, and my bit of pin strip there for the power distribution. So this is going to come over and it will go to connectors that are wired to here. The only thing I haven't really got space for is the power switches. I'm not sure where to put them at the moment. I might have to build another layer on top of here and put them in front, but that's only a minor issue. The power regulators from the servos are going to go and attach to the side of the servos. The IMU will go on top. The Bluetooth receiver can float around near the Arduino, which is mounted on the other side. So there's the Arduino Mega with the third motor driver and a little bit of pin strip. And the batteries on this side are the ones wired in parallel, so it makes sense they need less terminals than the one that's wired in series, and all that wiring with the power switches will happen on this strip. So that looks pretty good. I've got one thing that I've forgotten to put in so far. Now these are removable. If I take away this strip, I can get to the panel and take all the electronics out, so I can get right inside down here. So what we've got missing is some means of measuring how much tilt we've got in the trousers, which this whole thing, the batteries, the electronics, everything tilts side to side to shift its mass. But we need to know how much tilt there is on that axle that runs back to front relative to the outside, which is the banana piece, which drives along and doesn't tilt along with the ball. So somewhere we need to fit a potentiometer in there, which obviously changes resistance as it rotates. I'm going to use this. You could use a rotary encoder, but we need some means of getting feedback to know what the position is so we can accurately control it. So this rotates, as I say, so ideally we'd stick it, you know, in line with the axle, but we can't really do that because the axle runs all the way and there's no space. So all I'm going to have to do instead is build a clever mechanism where this, if I can just get my hand in, sits above the axle, and then a lever sticks out of the axle and out of the pot, and those are then linked with a sort of vertical lever so that turns the pot as this rotates against the axle, which is stationary. And that looks a bit like this. So what we've got here is the bit of the CAD there. This is the yellow parts, of course, the bits of the trousers and the banana and the axle through the middle. So first of all, I've got this piece. So the axle is actually pretty loose in this end coupling, and it can actually rotate independently, although it shouldn't because the trousers are mounted on bearings. If it slips at all, that'll put the pot out. So first of all, I've made this plastic piece, and that's going to be solvent welded to the yellow piece, so I can still get the red piece out to remove the axle if I want to, and it's also going to be cable tied onto the axle, so that should give me a stationary reference point about the banana. And then at the top here on the trousers, we're going to have this pot mounted exactly above them. That's mounted to screw holes that already exist. I've also put in mounting points here for the inertial measurement unit to screw onto, which should be exactly the right size and spacing. And a piece that screws on that holds the potentiometer. And then from there, we've got a leverage point down here, where the vertical lever will go, and then it will travel horizontally to a clamp on the pot shaft. So that should be everything, and we're going to print these parts, and then I can get the levers exactly the right length once they're installed. So here's the first part. I've got the screw hole in the end there, and this fits in just there. Try and keep my hand out of shot, and it solvent welds in just where my thumb is there, and then obviously the hole's cable tight around the axle. So I'm going to try and get that fitted. I'm going to solvent weld it in and then put the cable ties on. Alright, so here's the almost finished mechanism. It just needs fitting. So I've got this crank here, and when it moves up and down, obviously it turns the pot arm, and you'll notice I've got a captive nut there and a little screw so I can adjust this and move it around. But basically the flat of the shaft here is facing this, which means it's in the middle. It rotates more than enough in each direction. In reality, it's only going to do 20 degrees, the same as this. And that hopefully fits right in here. You can see this other screw, which I can just about get my screwdriver into like this. So I can do it up. And this should sit on top of here. I just need to hone that screw. Then hopefully that will move as the banana and trousers move against each other. And you'll notice I've left these mountings, as I say, for the inertial measurement unit, which is this, which you can see has got two holes in that match on there, so I can put one of those on once it's mounted. And I've remembered to attach wires to it already. The wire only has to reach the Arduino here, but I thought it was good to have a bit of extra length, and it'll save me trying to solder it once it's fitted. There is my mechanism all fitted, so I'm now going to try moving side to side and see what happens. So I have wired up a multimeter to 2 pins on that pot, which currently says 43 ohms. It's a 100k pot, so the thing's not quite in the middle at the moment, but that's roughly in the middle, of course, of 0 to 100. And if I just get a battery connected and we tilt it over one way, hopefully you can see that mechanism has moved, and the meter now says 51, so it's 10,000 ohms higher. And if I move it back the other way, in fact we'll move it all the way, hopefully you can see that mechanism moving. Hey. And now we've got 32 ohms, so nearly 10,000 ohms less. So I can use that to build a potential divider and read the value to an analog in of the Arduino. Let's just put that back in the middle. Obviously with the batteries mounted and everything moving side to side, this thing's got quite a lot of mass to throw around, so hopefully we'll be able to make that super stable. But what about stability now all the mass is in the ball? So obviously this is still quite happy to stay upright. To note that the ball isn't perfectly smooth, there's still a few ridges in it which it rocks on, but once the skins are on, like version 2, that will go away. But obviously it wants to stay upright most of the time. It's pretty stable, so I should have no problems dampening that electronically by moving this mass side to side and driving backwards and forwards, so I'm feeling pretty hopeful about that. That's the end of this video. Next time I'm actually going to wire some stuff up and write some code. And the first thing I want to do is try and make this balance sideways, because that's a bit of a tricky problem. Obviously driving forward and back, it can just drive to catch up to kill the wobble, but it can only move a limited amount sideways, so it's going to be interesting to see how that works out. And I think I'm going to need cascaded PID controllers. So don't forget to subscribe to my channel to check out more updates on this project, and also check out the other projects and the social media links in the description to this video.